Today's notes are on operations with radical expressions. So combining radical expressions, this just tells you that if you have two separate radicals and they have the same index, then you can combine them to one single radical. For example, if you had the square root of 2 times the square root of 2, remember we don't write the index of 2, but it does exist. So because these indexes are the same, we could combine this to the square root of 2 times 2, which is equivalent to the square root of 4, and the square root of 4 is 2. So the different forms is what you need to pay attention to. You can have separate radicals, you can have a combined radical, and of course your answer. Another example could be a cube root. If you had the cube root of 3 times the cube root of 9, you can't simplify either one of these, but what you could do is you could rewrite this as the cube root of 3 times 9. The cube root of 3 times 9 is the cube root of 27, and now you can simplify this. Therefore, the cube root of 27 is 3. So the big takeaway on this section is just that the index must be the same. And when I say index, we're talking about this number. Okay, we're going to start off with multiplying radical expressions. This is a lot like simplifying, so it's going to be similar to the last example set we went through. Every time you're multiplying radical expressions, you have to make sure that you are looking at the index, and in this case, the index is the same. Because the index is the same, you can multiply these together. This would give us the cube root of negative 4 times 2. The cube root of negative 4 times 2 is negative 8. And negative 8 is a perfect cube. This simplifies to just the value of 2, negative 2. Negative 2 is your solution. Okay, you would not have got that answer if you left it in its original form. So taking this form, going to this form, or the form of combining the radicals, is what allows you to answer the problem. Number 2, check your indexes. We have an index of 3 right there. We don't see it, but this is an index of 2. We cannot multiply these together. For the next example set, now we're multiplying more complex expressions together. So in this example, we have the square root of 72 times x to the third times y squared multiplied by the square root of 10 times x times y cubed. So you could approach this two different ways. You could simplify each root individually and then multiply your common terms together and keep working through the answer. For something like this, I know it's going to give us a large value, but you will cut down on terms or you will cut down on steps if you just multiply everything together to start with. So that's what I'm going to do. I think that it does end up being a little bit faster. We multiply our like terms, so we can multiply 72 and 10, which gives us 720. X cubed times x is going to be x to the fourth, and y squared times y to the third gives us y to the fifth. Now we need to take a look at our simplifying process, starting with the square root of 720. Well, 720 is not a perfect square, but if you make a list of all your perfect square factors, which you should all do down the side of your paper, The square root of 720 simplifies to 144 times 5. X to the fourth can be broken down into two groups of 2, and y to the fifth is two groups of 2 and one group of 1. Now I'm going to highlight everything that we can simplify. We know the square root of 144. We know we have the square root of x squared again. We can find the square root of y squared again. And then the remaining two factors, 5 and y, will remain underneath the square root symbol. When we simplify the square root of 144, the answer would be 12. 5 is going to stay under. X squared is x. X squared is x. Y. Left over is 5 times y. When we clean this up, we have 12 multiplied by x squared times y squared times the square root of 5y. Okay, now you can do some of this in your head, and I'm completely fine with that. So you don't have to show every single step. Of course, some steps are definitely necessary, but you can skip a few in here and get to the same answer. For number 2, I'm going to do the same thing. I am going to multiply everything together. 45 times 35 is 1575. So for this number, you guys are going to have to increase the list of your perfect squares. This is quite a large factor, so it's going to have a large square factor multiple that you're going to use to simplify. X to the fifth times x is going to give you x to the sixth. And y to the third times y to the fourth is y to the seventh. You should check your list for perfect square factors. I know that the largest perfect square factor is 225. This is going to be 225 times 7. X to the sixth is 3 groups of 2. And y to the seventh is 3 groups of 2 and 1 group of 1. Highlight the terms that we can simplify. When I simplify this, the square root of 225 is 15 times x times x times x times y times y times y. Left over is 7y. Your final answer is 15 times x cubed times y cubed times the square root of 7y. All right, for the next part, we are combining radical expressions using division. So there's quite a bit to division. There's actually so many different ways you can simplify. You have to be mindful of all the different methods, and you have to figure out which one works best for whichever problem. So right here, this is the same idea as what we went over above. Basically, it's telling you that if you have two radicals that have the same index, then you can either leave them as two separate radicals, one in the numerator, one in the denominator, or you can combine them to one single radical with a fraction underneath that sign. It doesn't have, or there isn't one or the other that is more correct. It just depends on the problem. So you're going to have to go between these two forms in order to solve these problems. If I was to give you an example of this, we could start with the square root of 27 over the square root of 3. So we don't know the square root of 27, and we can't simplify the square root of 3. But if we convert this to one single fraction underneath the square root sign, we have 27 over 3. That simplifies to the square root of 9, And then we do know the square root of 9. We know that it's 3. So without converting to one single fraction or one single radical, we would not have arrived at our answer. Now, on the other hand, we have the cube root of x to the 6th divided by 8. Now, x to the 6th does not divide into 8. We cannot simplify this in any way, so this at that point is all we can do. But if we break this apart to two separate radicals, the cube root of x to the 6th divided by the cube root of 8, in the numerator, the cube root of x to the 6th is the same thing as x cubed times x cubed, and in the denominator, the cube root of 8 is 2 cubed. This simplifies to x squared in the numerator divided by 2 in the denominator. So without breaking this into two separate radicals, then we would not have arrived at our answer. Two different types of problems, two different forms. So for number 1, we have the square root of 18 times x to the 5th divided by the square root of 2 times x cubed. You can simplify parts of each of these, so go ahead and do that if you want. But if you convert this to one single fraction, I instantly recognize that 18 divided by 2 is 9, and 9 is a perfect square. So that's definitely going to help us if we start with that. I'm going to take this fraction and I'm going to write it as one single radical. Underneath the radical sign, I have 18x to the 5th divided by 2x to the 3rd. Now I'm going to simplify that fraction that's underneath the sign. I know that 18 divided by 2 leaves me with 9 in the numerator. And x to the 5th divided by x to the 3rd, well, you eliminate your exponent of 3, and the exponent of 5 becomes 2. 5 minus 3 is 2. So in the numerator, we're left with x squared. Our denominator is just 1, which we do not need to write. Now that we did that, we have this radical. The square root of 9 is 3, and the square root of x squared is x. 3x is your final answer. Number 2. We have two cube roots. Always check your index, make sure you can simplify. Again, we can simplify a few things. Not sure that it's going to be super helpful, so I'm going to start by creating one single radical, and it's going to be the cube root of 162 y to the 5th divided by 3 y squared. And here I'm going to eliminate this fraction because I know 3 goes into 162 54 times. And I know that y squared and y to the 5th will simplify to y to the 3rd. The cube root of 54, y to the 3rd. Now, 54 is not a perfect cube, but if you're looking at your perfect cube list, then you know that 27 is a factor of 54, and it would be 27 times 2 times y cubed. 27 simplifies, and y cubed simplifies. We end up with 3y times the cube root of 2. For the next example set, we're going to talk about rationalizing the denominator, which is a very big topic for the upcoming lesson. So this lesson, but also lessons in the future. So to eliminate radicals from a denominator or fractions from a radicand, you can use the process called rationalizing the denominator. To rationalize the denominator, you multiply the numerator and the denominator by a quantity so that the radicand has an exact root. Let's take a look at a very basic example. If I gave you the example of 2 divided by the cube root, let's do the square root of 3. You cannot have a square root in the denominator based on what I just read you. So in order to eliminate what's going on here, you are going to multiply both the numerator and the denominator by a value of 1 that is going to eliminate that square root in the denominator. So there's two things you can do. You can multiply it by itself, which always works, and that's what I recommend. Or you can multiply it by a value that's going to get it to the closest perfect square, in which it will simplify. You'll notice that I always multiply it by itself. So starting with that, I recognize that the square root of 3 is in the denominator, so I'm multiplying both the numerator and the denominator by this value. That's what we're doing. This here creates a value of 1. So doing that now gives me 2 square root of 3 in the numerator, and the denominator is now the square root of 9. This is exactly what we were trying to get. The square root of 9 simplifies. We have 2 times the square root of 3 divided by 3. So we never want a square root in the denominator. Do whatever you have to do to eliminate that square root. If we looked at a more complex example, let's do a cube root. Let's say we had 5 divided by the cube root of 2. Now this one's a little bit different. It's not as easy as the square root. You can't exactly multiply it by itself because that doesn't always work. Because the radicand is 3, that means we need to make groups of 3 underneath that radical symbol. So this is technically 2 to the power of 1. Because we need to make a group of 3, I'm going to multiply both the top and bottom by the cube root of 2 squared. 1 plus 2 equals 3. That's how I came up with that value. Multiply the top by this number as well. The numerator becomes 5 times the cube root of 4. The denominator becomes the denominator becomes the cube root of 2 cubed. That's what we were looking for. We originally had 2 to the power of 1, multiply it by 2 to the power of 2, now we get 2 to the power of 3. This simplifies to 5 times the cube root of 4 divided by 2. All right, for the next section, we're just doing some more examples of these. Number 1, we have x to the 6th divided by y to the 7th. We can't simplify because 1's a variable of x, 1's a variable of y. Break this apart to the square root of x to the 6th divided by the square root of y to the 7th. We need to rationalize. So to do this, we know that the index is 2. I guess we'll do this one kind of like we did the last example. If the index is 2, then we're going to multiply it by whatever value to make a perfect group of 2. Here our index is 2, our exponent is 7. The next perfect group of 2 would be 8. So I'm going to multiply both the top and bottom by the square root of y to the first power, which we don't really need to write, but y to the first power. That way, when I multiply my denominator out, I end up with the square root of y to the 8th, which is a perfect group of 2. My numerator is x to the 6th times y underneath my square root sign. Now I need to simplify this. So in the numerator, x to the 6th, that's 3 perfect groups of 2. That means what's going to simplify is going to be x to the third times the square root of y. In the denominator, y to the eighth is 4 perfect groups of 2, so that's going to be y to the fourth. For number 2, we have the cube root of 3x divided by the cube root of 12x. All right, in the denominator, we have, actually, you know what I'm going to do here? I'm going to simplify this first because I do notice that some terms divide out. So I'm going to simplify this by changing it to one single fraction and see what I can do from here. So if I do this, I notice that the 3 will simplify with the 12, leaving a value of 4 in the denominator. And both values of x will be eliminated. This leaves me with the cube root of 1 over 4. All right, from here, I can't really do anything else, so I'm going to simplify this back to 2 separate radicals. I have the cube root of 1 divided by the cube root of 4. Note that the cube root of 1 is 1, so I'll change that in the next step. As for the denominator, this is technically 4 to the power of 1, so I'm going to multiply both the top and bottom by the cube root of 4 to the power of 2. That gives me that group of 3. Don't forget that I can simplify that numerator. So my new numerator is the cube root of 4 squared, and my new denominator is the cube root of 4 to the third. When I simplify this again, I have the cube root of 16 divided by 4. Now the cube root of 16 can be simplified because 16 has a perfect cube factor. This would be the cube root of 8 times 2, and the cube root of 8 is 2 times the square root of 2. So bring that back into the equation. My next step would be 2 times the cube root of 2 divided by 4. And the only other thing I can do here is recognize that 2 and 4 can be simplified. 2 goes into itself once, goes into 4 twice, for my final answer of the cube root of 2 divided by 2. Next, we need to talk about the conjugate. So what is a conjugate before we even start these examples? So the conjugate is where we change the sign in the middle of the two terms. For example, if we had 3x plus 1, the sign is plus 1, so the conjugate would be 3x minus 1. These two are considered conjugates. If I gave you another example, if I gave you, let's do negative 4x plus 6. Actually, let's do minus 6. Oops. The conjugate would change the sign in the middle, only the middle, so our conjugate would be negative 4x plus 6. So in this next step, we are rationalizing the denominator using the conjugate. And the reason why we're using the conjugate for this denominator is because it has an addition or a subtraction sign included with it. So you can't just multiply by the radical because there's more to the denominator than the radical. For number 1, 4x divided by 3 minus the square root of x. If we're multiplying by the conjugate's going to be 3 plus, that's the opposite sign, the square root of 6. And you do that for both the top and bottom. Remember that this is in parentheses because you have to make sure you distribute. For the numerator, we distribute 4x to both terms, giving us 12x plus 4x times the square root of 6. And for the denominator, you distribute your first terms and then your second terms. 3 times 3 is 9. 3 times the square root of 6 is positive 3 square root of 6. Negative square root of 6 times 3 is negative 3 square root of 6. And negative square root of 6 times the square root of 6 is negative square root of 36. What we just created is this middle term that's going to be eliminated. That's what we purposely did. That's what the conjugate does. This right here is going to be simplified. Also, we know that the square root of 36 is a perfect square. That's something else that we created. So we end up with 12x plus 4x times the square root of 6 divided by 9 minus the square root of 36, or 9 minus 6. And for our final answer, 12x plus 4x times the square root of 6 divided by 3. And for anyone wondering why we don't divide out common terms or add like terms in the numerator, that's because 4x times 6 is a factor of its own. The only way you could add anything to that is if it was the same exact form, so it was still a number times x times the square root of 6. That is not the case, so you cannot simplify this any further. Number 2, we have a denominator of the square root of 5 minus the square root of 2. That tells us that we can multiply this by the conjugate. That's going to be the square root of 5 plus the square root of 2. Because we do that to the denominator, we're also doing this to the numerator. When you simplify, distribute 3 times the square root of 2 times the square root of 5, you can only multiply together your square roots. The 3 will remain as a coefficient, so you end up with 3 times the square root of 10. 3 times the square root of 2 times the square root of 2. That's going to give you 3 times the square root of 4. In the denominator, square root of 5 times the square root of 5 is the square root of 25. Square root of 5 times the square root of 2 is positive square root of 10. Negative times the square root of 2 times the square root of 5 is negative square root of 10. Negative square root of 2 times the square root of 2 is negative square root of 4. There's quite a bit that we can simplify. I'm going to start by indicating those terms are going to be eliminated. They form a value of 0. But besides from that, we have the square root of 4, we have the square root of 25, and we have the square root of 4 again. This becomes 3 times the square root of 10 plus 3 times the square root of 4, or 3 times 2. That's going to be 6, divided by the square root of 25, which is 5, minus the square root of 4, which is 2. This gives us 3 square root of 10 plus 6 divided by 3. And for the on your own section, I'll complete the work here if you want to just follow along. Any questions, send me an email.